Hi everybody, we made it to the last chapter of the course. We're in chapter 13, talking about the F distribution and one-way ANOVA. So, the basic idea behind this chapter is what we've been doing is running hypothesis tests on a single value, a single parameter, either a mean or a proportion, and then we've been comparing two different means or two different proportions. That's what we did in kind of the last couple chapters. Excluding chapter 12. But now, for chapter 13, and kind of beyond chapter 13, we can use these tests here to be able to run hypothesis tests on multiple means, being 3 or more. So this is really useful in practical application because you oftentimes have 3 or more factors that go into a single calculation statistically. So we need to be able to work with them simultaneously instead of running, 10 different hypothesis tests. We'd like to just run one that compares all these values. So the first up, we have the one-way ANOVA. So ANOVA is just an abbreviation for analysis of variance. This is an inferential method used to test the equality of 3 or more population means. So we have 3 or more population means. So for ANOVA, the null hypothesis is always that the means of the different populations are equal, right? That's our status quo. We just say, yeah, they're all the same. All the means are the same. And the alternative hypothesis is always that at least one mean is different from the others. Okay, so we go in with the assumption that all the means are equal, and then we try to find evidence to support the claim that actually at least one of those means is different from the others. Okay. Now, like I mentioned, we don't want to be performing multiple hypothesis tests here because that's going to not only be ineffective in terms of our time, it's also going to be very ineffective in terms of our possibility of making an error. So the probability of making a type 1 error is actually much higher if you run multiple hypothesis tests on this one condition. So this test is actually going to be more accurate than doing that. Okay. So a few requirements to perform a one-way ANOVA. So there must be k simple random samples. Okay, one from each of the k populations or a randomized experiment with k treatments. The k samples are independent of each other, so subjects in one group cannot be related in any way to the subjects of another group. The populations are normally distributed. They must have the same variance, okay, so the same population variance, and the factor is a categorical variable, and the response is a numerical variable. Okay, so just a brief rundown on kind of what that ANOVA does. Okay, so let's go ahead and look at the F distribution. This is how we're going to be working with ANOVA. So the F distribution, also known as Snedekor's F distribution or Fisher's distribution, Fisher is where the F comes from, is a continuous statistical distribution which arises in the testing of whether two observed samples have the same variance. So the idea in one-way ANOVA is to determine if the sample data could come from populations with the same mean or suggest that at least one comes from a population whose mean is different. So we need to compare variability among the samples and compare that to the variability within each sample. So we have two different types of variability that we're looking at here. There's between sample variability and within sample variability. Okay, so when we're talking about the difference between these two, so let's say I have 3 different samples here, 3 different groups. Okay, well, then if we're talking about within sample variability, I'm talking about the mean of the values in this sample. So if you take a bunch of values from this one and you get their mean and you calculate whatever that value is, and you look at this one compared to this other one within the sample, then we have variability there. Okay, there's going to be some variety among the different values within each sample. And when we talk about between sample variability, we're talking about what is the value I get out of this whole thing, and I'm going to compare that to the value of this one, and compare that to the value of this one. Okay, so when we're talking about within sample variability, we're talking, as it says, within one sample. Okay, so within each sample itself, how much variability does it have? And then the between sample variability, how much variety, how much change is there between the different values, okay, of the different samples. Okay, so, and the conclusion we can draw, so if the between sample variability is large relative to the within sample variability, we have evidence to suggest that the samples come from populations with different means. Okay, so in other words, if the variability, the differences between the samples is really large compared to the within sample variability, then that gives us strong evidence. Okay, because if the within sample variability is very small, so within my sample here, all these values are pretty close together, right? That would mean there's very little within sample variability. But then if I compare that to this one, and all these values are vastly different between each other, then that means the between sample variability is very large. So that would indicate that we have different population means. Okay? Whereas if I get all the values within this first sample, and I get all the values within the second sample, and they're all relatively close to each other, and the between sample variability is pretty low, then we would not have strong evidence to conclude that the means were different. Okay, so we take both of them into account. So the analysis of variance F-test statistic is given by this ratio. So F naught, that is the between sample variability divided by the within sample variability. Okay. So first example here, as part of an experiment to see the way different types of soil cover would affect slicing tomato production, Marist College students grew tomato plants under different soil cover conditions. Groups of 3 plants each had one of the following treatments: bare soil, a commercial ground cover, black plastic, straw, compost. All plants grew under the same conditions and were the same variety. Students recorded the weight in grams of tomatoes produced by each of the 15 plants. Create the one-way ANOVA table. So here we have an ANOVA table. Okay, so and I'll show you guys in a little bit how we can make these. But this gives us pretty much all the information that we need to run our hypothesis test. And all we need to do is input this data into a table. Okay, and I'm going to be using Excel in a little bit to do that. So, but that's what our ANOVA tables are going to look like. But you can see here, we've got the different groups here, how many in each group, their sum, their average, their variance. Okay, so we get all that information, and then we get the ANOVA information that we're going to need. Okay. So some facts about the F distribution. So the curve is not symmetrical, but skewed to the right, so it shares that in common with like the chi-square distribution. There's a different curve for each set of degrees of freedoms. And the F statistic is greater than or equal to 0, so it's always positive. And as the degrees of freedom for the numerator and denominator get larger, the curve becomes approximately normal. Okay. And then other uses for the F distribution include comparing two variances and two-way analysis of variance. But we're not going to get into all of that. But basically, you can see the F distribution, it kind of behaves like chi-square, so a lot of these properties are the same. But it is slightly different. There's a little more going on here in the F distribution. Okay. So when it comes to testing a hypothesis around 3 or more means, we need to determine if there's enough evidence to support the claim that at least one is different than the others. So the null hypothesis is always that the means are the same. The alternative is always that at least one is different from the others. Okay. So a brief note about the use of ANOVA. So the methods of ANOVA are robust. So what that means is that it can stand up even without strict normality. Okay, so even if we're slightly moving away from normality, we're not quite normal, it's not going to really change that significantly what the procedure does for us. Same idea, the requirement of equal population variances does not need to be strictly adhered to, especially if the sample size is the same. So even if we don't quite have normality, we don't quite have the same variance, the test is very powerful in that way. We don't need to have those things in order to run the test successfully. Okay. So the one-way ANOVA procedures may be used if the largest sample standard deviation is no more than twice the smallest sample standard deviation. Okay, so we can look here at this example. So the following data represent the weight in grams of pennies from 90, 95, and 2000. And we can verify the requirements in order to perform the one-way ANOVA are satisfied. So you can look at kind of the variability in these different box plots, so you can see how spread out the data is with no outliers. And then if they run the probability plot over here, you can see everything we need right there, and you can look at the standard deviations in particular, or what they wanted to point out. So there's the first one, the second one, and the third one right in there. Okay. And notice our sample sizes, 11, 11, 11. Those are all equal as well. Okay, so those conditions that they're talking about, those are all satisfied appropriately. So let's take a look at example 13.1 and test the claim that at least one population mean weight in grams of tomatoes is different. So let's go back and look at this, but if you want to keep your page right here, then you can do writing on this one. But let me go back to the example. Here it is. Okay, so we want to run hypothesis test on this. Well, the hypothesis test is that, right, so H naught R null is that all three are equal. And the alternative is that at least one different. Now when we're running a hypothesis test, right, we get our test statistic, we look and we compare it to either the critical value, or we can look at the p-value and compare that to alpha. So if you look down here in this table, on the right hand side here, this value, this is f, this is our test statistic right here. So it gave us the test statistic, and it gave us the critical value, and you can see using that test, our test statistic is larger than the critical value, so it lies in the critical region, which means we reject the null, which means there's at least one different. Or you can just look at the p-value and look at the p-value and say, okay, 0.025 approximately, that's about 2.5%. So if we're assuming our alpha value is 0.05, which typically if it's not specified, that's what we do, we assume alpha is 5%, that would give us a value smaller than alpha, which means we reject the null, so we say at least one of these means is different. At least one of the population means is different. Okay, so we're reading that all from down here. So let me get back to this space here. So we saw that the p-value was approximately 0.025, which is less than 0.05, which is alpha. And again, it didn't specify anywhere in here what alpha is, and when that's the case, we just assume it's 0.05. Okay. Also, we can make a note that the test statistic was 4.48, which was greater than 3.48, which is, f sub alpha. Okay, so that tells us it's in the critical region, which we've seen in our hypothesis test before. So we can reject the null hypothesis, and we can say at least one population mean is different. Okay. All right. So now, when it comes to doing the penny example down here, we're not going to go through the whole process together here, because this one, typically we do this one manually, but I'm just going to show you guys kind of how we would set this up. So, with the mean weights of pennies at the 0.01 level of significance, test the claim that at least one of the mean weights is different. So our null hypothesis, as it always is that the means are the same. And our alternative hypothesis is at least one mean is different. Okay. So a few things we would need. We would need to get the means of each of these values, of each of these data sets. So that would be from here. So from this table. We would get the mean of each of these. We would get the mean of the whole thing. And we would also get the variance of each one. Okay. So if we were to do that, so the mean of the 90 data, that's 2.496, and the variance is 0.000485. Okay, and then the second one, we have the mean is 2.509, and the variance is 0.000589. And these are all numbers you could just get from Desmos, right? Just input the data set into Desmos and then type mean of the data and variance of the data, and it would give it to you right away. And then the third one has a mean of 2.5, so pretty simple there. And then it has a variance of 0.0002. Okay, so what we would do if we were doing this by hand is we would get the between sample variability, and we would divide it by the within sample variability. That would give us our test statistic of F naught would be point really small, 1, 2, 3, 4 zeros, and then 4898. And then the fact that the test statistic is so small would tell us that the sample means are not going to differ from each other, so the population means we have strong evidence to suggest that we do not reject the null hypothesis. So we would say that there is not sufficient evidence to conclude at least one mean is different. Okay. So again, don't worry too much about especially this part of the computation, because we're not going to be doing that by hand. This is just to give you an idea of kind of the layout of these ANOVA tests. Okay. And then last example, so a researcher wanted to determine the effectiveness of various treatments on glucose levels of diabetic rats. The rats were put into 4 treatment groups and given the diet supplement implied by the table below. The researcher wishes to determine if there's a difference in the mean glucose among all 4 treatment groups. Test this claim at the alpha equals 0.05 level of significance. So this one I went ahead and did on Excel. So let me just pull that up. What's it doing? There we go. Okay. Here it is. So what I did was I went ahead and inputted all of the data. Okay, and then you can see over here I have my ANOVA test. So in order to get this ANOVA test on Excel, so if you're using Excel and you don't have it, so it would be in data, but it would be under data analysis. Okay, so if you want to just make a note of that, it would be under data analysis. Okay, so and if you don't have it, it is just an add-in for Excel, and it is completely free. So all you would need to go into the add-ins section under File, I believe it is, on your Excel on your computer, and it would just be the add-in for statistics and for analysis. Okay, so I think it's like analysis. I forget what it's called, but I'll go ahead and put an image down in the module to help you get there. So anyways, but once you do that, you get to this table. Once you have the table, this pretty much gives you everything you need. So it gives us the between group and the within group variances. It gives you the test statistic, it gives you the critical value, and it gives you the p-value. Notice test statistic is hugely greater than the critical value, and the p-value is incredibly small, right? 3.744 times 10 to the negative 12th power, so that's move the decimal place to the left 12 places, so it's going to have 11 zeros in front of it. Incredibly small value at any alpha value, right? That's going to be incredibly smaller. So what does that tell us? Well, that tells us that we have very sufficient evidence to reject the null hypothesis. So in other words, there is sufficient evidence to conclude that the population means for these different samples are different. Okay. So again, I'll post a little kind of how-to if you want to try to get that Excel add-on in the module, so you can take a look at that. But that's going to be it. That's it for Chapter 13. That's it for new materials. So congratulations on making it to the end of the course. When we come back next time, we'll have a bit of review for the upcoming exam, and then we turn our attention towards the final. So great job sticking it through all the way. We're almost done, and I'll talk with you all next time.